Hello everyone, welcome back to another video. Today we are going to be looking at the controlled volume of a certain type of substance, and we are going to be looking at how heat is going to diffuse through this specific volume of that substance. Alright, so we are going to be having a heat flow into this controlled volume through the left face of the volume, and then it is going to be coming out on the right side of the volume. And we're going to be looking at how the heat diffuses as it enters from this left side and leaves through this right side. And this is going to be pretty simple to start. So pretty much this heat diffusion is just going to be a pretty simple energy balance. It is going to be the energy going into it, this Qx right here, minus the energy going out, our Qx plus dx. And then that is also going to be added by the energy generated within this controlled volume, and that is going to equal the energy stored within the controlled volume. So we'll go ahead and write that out now. So we had E in minus E out plus E generated equals E stored. Alright, so now we're going to have to come up with some different expressions to represent all these different energies right here. And the first one we're going to do, and the simplest one, is going to be our energy N right here, this En, and that is just simply going to be Qx, our heat flowing into the controlled volume. Alright, next we'll go ahead and take a look at this E out right here, and pretty much this E out is just going to be this heat flowing out, and then we are also going to have to account for how that heat is going to be changing as the x direction changes, alright? So E out, we'll go ahead and write E out over here. E out is going to be equal to our Qx, and then we are going to have to account for how that heating is going to be changing as we change in the x direction. So that is going to be represented like this. And then, of course, we are going to have to account for our differential change in the x direction still. So we'll multiply this by dx. So this is going to be our E out right here. So we'll go ahead and write that up right here. All right. And then over here for our E generated, that is simply going to be represented with a rate. So we'll say E rate. So EG right here, and we'll use this dot to represent the rate. And then this is just going to be equal to the Q rate. So the rate of heat, and then this is going to be multiplied by the differential volume, this whole volume right here, and that's not just going to be dx, we're going to have to use dz and dy as well in order to get the differential volume. So we could write this out as q dv, but we're going to go ahead and write this out as dx, dy, dz. Those are the same thing. dv is equal to dy, dx, dz. So we'll go ahead and write that out. This is going to be our energy stored, or excuse me, our energy generated within our controlled volume. So this is going to be Q dy, dz, dx. This is a Q, not an A. Alright, and lastly, we are going to have our energy stored within our controlled volume right here. And for that, we are going to say that that is going to be equal to the density times the heat capacity to start. So we'll go ahead and start writing that out. So this is going to be equal to the density of whatever substance or compound that this controlled volume is. This could be anything. This is whatever you want. So that is going to be the density multiplied by the specific heat of that substance, Cp right here, and then that is going to be multiplied by the change in temperature as it relates to a change in time. And then once again, we are going to be multiplying by the differential volume, this whole cubic volume right here, dV. And that is going to be right here, our expression for this energy stored. So it looks like we ran out of room a little bit right here. So we'll just go ahead and write out this whole thing. Okay, so we've written out our equation right here to represent the heat diffusion through our controlled volume right here. We've gone ahead and substituted in our expression right here for the energy stored, so we'll go ahead and erase that. Alright, and now what we can do now is start simplifying this down so it looks a little easier. The first thing we can do is we can see that we have a QX minus a QX right here, so those will go ahead and cancel out. And then we also need to not forget that this is subtracted, so we need to go ahead and make this a negative over here. So we'll just go ahead and erase that and make this a negative. Alright, and then we can get rid of our parentheses. Alright, and the next step we are going to make is we are going to be using Fourier's law to come up with an expression for our QX right here. And basically what that is going to say is QX is going to be equal to the heat flux right here. This is being used to represent the heat flux through the x direction multiplied by the area. And then what Fourier's law says is that this heat flux right here is going to be equal to negative K, alright, and then this K is the conductivity of the material that is going to be in our controlled volume. That is the conductivity right there, and then that is going to be multiplied by the change in temperature as it relates to the change in time, right? And then this is going to be multiplied by the face through which that heat or energy is being transferred through, alright? So this is going to be our left side face of the cube right here. And in order to get the volume, or the area of that, it is just going to be dz right here, our inward looking vector, multiplied by our height, which is going to be our dy. So this is going to be multiplied by dz dy. And then, of course, this is going to be our representation right here that we're going to use for our QX right here. Alright, so next we can go ahead and plug that in, and we'll go ahead and do that now. We'll plug this in for our QX right here. So we will get negative change, and then this will be negative K, change in temperature, change in time, and then this will be dz dy. This is what we are plugging in for QX right here, and then this was all over change in x, and we had a negative right here and a negative right there, so those negatives are going to cancel out, so we're not going to have to worry about that. And then we also had our dx out front. Don't want to forget about that. Now looking at this, we can see that this dz dy dx right here, that is just going to be our differential volume, our controlled volume right here. So we can simplify that down to dv. And again, that is not going to be changing with respect to all this heat transfer that's going on. So we can bring that out of our differential equation out to the front. And then once we do that, we can see that we also have another dy dx dz, which is again just a dv, and that can cancel out because we have a dv over here. So we have a dv on every part of our equation, so we can go ahead and divide everything by dv and cancel all that out. So we are not going to have to worry about that. Alright, our next move is going to be to bring this k out of our differential equation, because that is not going to be changing with relation to any of this. So we can go ahead and bring that out, And I don't think we should have this negative in here because this is just that negative, and that cancels out with our negative from the start of the equation before we substituted this in for qx. So we can erase that and just bring the k out. Alright, and then this differential is just going to become a secondary differential. So this is just going to become squared t over change in x squared, like so. This is going to be our second degree differential over here. And then over here, we would just have q plus our q rate. And then dv got canceled over here as well. My q's are looking a lot like a's today. We'll go ahead and make sure we know that's a q. So we had the density times the heat capacity times our change in temperature over our change in time. All right, we'll go ahead and erase all of this right here. Clear up a lot of space for ourselves. Getting a little hectic. Alright, so now what we are going to want to do is we are going to want to divide everything by 1 over k. Alright, and when we do that, this k is going to cancel, this is going to become q over k, and then again this is going to be divided by k as well. So we'll go ahead and write that up. Try to make it nice and big so I'll make sure you guys can see at home. Plus q over k. Alright, and the reason we did this is because there is going to be a term represented by this symbol right here that is going to be equal to the inverse of this, which is our conductivity over the density multiplied by the heat capacity. And pretty much what this symbol represents as a whole is how this heat is going to diffuse through this through our specific volume right here. So say you had a flame over here and you wanted to see how the heat is going to diffuse and what rate it is going to diffuse at. This is the symbol that represents that relationship right there. So this is going to be key for us, and we can go ahead and substitute this in over here. Of course, we would use 1 over since this is the inverse. So we can go ahead and write that up now. And there you have it. This is going to be our equation that we are going to use to represent the heat diffusion through the specific volume of our substance right here. And yeah, that is going to do it for today's video. I hope you guys enjoyed and learned something new today, hopefully. If you enjoyed the video, make sure to leave a like and subscribe to the channel if you want to see more content similar to this. And yeah, take care.